right, so what about the timing events in synaptic transmission? Calcium is essential for the release event at the presynaptic nerve terminal, but there's this delay between when the presynaptic potential arrives, it changes when the actual potential arrives at the at the presynaptic nerve terminal, and when the postsynaptic response occurs. And that time is due to numbers of factors. It could be due to the time it takes the vesicles to fuse, it could be due to the calcium, it could be due to the time the transmitter is needed to cross the cleft, it could be due to the activation of the receptors on the postsynaptic side. We don't think it's the latter because ionophorese acetylcholine on a neuromuscular junction produces a response absolutely immediately without any delay. And if one calculates the diffusion time across a 100 nanometer cleft, that's in the 50 to 100 microsecond time span. So that does not really account for the several milliseconds of synaptic delay that is seen in frog neuromuscular junction or at invertebrate synapses. And the experiment I'm going to talk about here was done by Rudolfo Linas and colleagues, and it was done at the squid giant synapse. So not only did the squid giant axon contribute to our knowledge of voltage-dependent ion channels, but the giant synapse inside the squid's cerebral ganglion gives us a large presynaptic nerve terminal, which is here on the bottom, and a postsynaptic structure, which is on the top. And both are large enough to get 2 microelectrodes into and voltage clamp. And in this particular experiment, postsynaptically we only needed 1 electrode for recording, and presynaptically Linas voltage clamped to maintain control over the presynaptic membrane. So if he holds the presynaptic membrane at minus 80 millivolts and steps to a positive 0 or a very positive potential, he can, in the right ionic conditions that have no sodium and blocking sodium and potassium channels, see an inward calcium current, which is recorded here in the presence of calcium. And when that potential is restored to minus 80 millivolts, the calcium channels close and one can see the turning off of that calcium current at that time. Postsynaptically, however, even though the calcium channels are turning on, there is a delay between when one gets this postsynaptic response. So it appears that the postsynaptic response is dependent on the timing of the onset of the calcium current. And to nail that, Linas does a trick with the voltage clamp. He steps from the holding potential at minus 80 millivolts to a very positive potential where the calcium equilibrium potential is. So at the calcium equilibrium potential, there should be no driving force on calcium, but the calcium channels themselves should be open. And under those conditions, there is no calcium current recorded. However, when the potential is then repolarized to the holding potential of minus 80 millivolts, calcium channels are still open instantaneously. They have not had time yet to close, and going back to minus 80 now puts a very large driving force on the calcium ion. So one gets instantaneously a very large calcium current, which then turns off. And under those conditions, we can make a line down here. The postsynaptic response, although smaller, is essentially instantaneous with this large amount of calcium current being turned on, indicating that the timing of the opening of the calcium channels is what is slowing the release event. And here he plots the timing not only of the presynaptic response and the postsynaptic response, but the timing of the presynaptic calcium currents. And one can see that they only, since they're voltage dependent, they only turn on after the presynaptic nerve terminal reaches a certain amplitude of depolarization. Calcium channels themselves and their regulation become very critical for the timing of synaptic vesicle release. One can visualize those presynaptic changes in intracellular calcium by using calcium-sensitive dyes, and this was done a lot in the 1980s. Here I'm showing a very beautiful picture taken by George Augustine and Steve Smith, again at the squid giant synapse, where the postsynaptic element is at the top and the presynaptic element is here. The presynaptic element has been loaded with the dye, Fura-2, which is a calcium-sensitive dye. And after presynaptic nerve terminal stimulation, one can see very high concentrations of calcium in red inside the presynaptic membrane leaflet, apposed to the postsynaptic site, and a decreasing concentration of calcium as one proceeds further away from the active zone and into other presynaptic, or upstream in the presynaptic neuron, suggesting that the control of calcium concentration inside the presynaptic nerve terminal may indeed be limiting for the release of transmitter. And one has to consider this since calcium does so many different things inside cells. There are lots of different calcium activated enzymes and processes. And indeed, that spatial distribution of calcium can be modeled and then demonstrated to be very restricted. We know that there are calcium binding proteins inside all cytoplasm. Some of these are calpain, calmodulin, calretinin, calbindin, parvalbumin. There's lots of families of them. And their presence inside the cytoplasm is what allows cells to regulate different calcium-activated events in very fine manner. These calcium binding events can be both high affinity with relative low capacity or low affinity with relatively high capacity. And where they are in the cytoplasm may be important, just as calcium sequestering organelles like the mitochondria or the endoplasmic reticulum can also be important in the binding of and chelating of calcium in the cytoplasm, the control of calcium. But the question really becomes at the presynaptic nerve terminal, do these cellular buffers affect calcium concentration locally in a manner that could regulate neurotransmitter release? And so Linnas went on to ask the question, what was the distribution of calcium around a single calcium channel? And if you just model a single calcium channel in the middle, say, of this dome, and think of the voltage-dependent channel opening and the large 4 order of magnitude gradient of extracellular to intracellular calcium driving calcium inside the cytosol, just by diffusion equations alone, one would expect this hemisphere of calcium to push its way basically into the cytosol. One should get equal distribution of calcium from this point source of an open single channel. Now, if Linnas added into his model, in addition to these diffusion equations, the presence of extracellular calcium chelators, that is, proteins to calcium chelate with different affinities and different capacities, under those conditions, opening the same single calcium channel produced a very different shape of calcium gradient with inside the nerve terminal. The model shows that the area inside the cytosol with increased intracellular calcium should be this very steep needle-like or conical shape, because any calcium coming in and moving slightly away would be rapidly bound by a calcium chelator from with a high affinity, and then passed off to a rather low affinity calcium indicator as distance moved away, and finally transported all the way to an organelle for sequestration. And the reason we get this conical structure is because the velocity of calcium coming in with this very strong gradient is much greater straight on the straight shot. So we have a very incredibly tight compartmentalization of calcium inside the cytosol without any delimiting membrane structures. And you can see the dimensions here in terms of looking at this just in 2 dimensions rather than a 3-dimensional plot. We're talking about calcium concentration dropping off within 10, 20, 30 or angstroms, so that would be quite, 30 angstroms would be 3 nanometers from the calcium channel itself. If you look at this in terms of the time after opening, you can see that again, as the longer a channel is open, the greater the concentration and the farther that calcium concentration would spread, so that even quite far away, one might have a little bit of calcium left, and this is what we call residual calcium lining the inside of the presynaptic nerve terminal membrane. And again, if one looks at that distribution after the channel closes, one can see that it takes a while for the calcium concentration to go back down towards normal or steady state, and that it can remain slightly elevated after a channel closure. Now, the other thing I want you to scale is the vertical axis. The peaks of these calcium domains actually in concentration terms can be quite high, several hundred micromolar. So we're going from an inside calcium concentration of 100 nanomolar, 2 orders of magnitude, maybe 3 orders of magnitude higher when a calcium channel opens, which is a phenomenal change in calcium concentration in a very, very localized manner that could be quite potent in terms of its ability to regulate vesicular, what we now know is vesicular release and of a neurotransmitter. All right, Linus went further and actually visualized these little bitty puncta of calcium influx inside the squid giant synapse, presynaptic nerve terminal membrane, by utilizing very sensitive calcium dyes. This is a version of aequorin, which is actually the first protein calcium binding protein that was utilized and discovered, and it fluoresces, and one can see very small puncta of fluorescent dye on the inside of this presynaptic nerve terminal membrane, indicative of these very small domains. Is there a scale bar here? These are basically in the 100, 200 nanometer diameter area. So, in summary, we've seen that neurotransmitter release is quantal in nature, that the idea that neurotransmitter is stored in synaptic vesicles and released in this packaged manner is well established by multiple methods, and that a substantial, highly localized influx of calcium inside the presynaptic nerve terminal membrane critically regulates the vesicle fusion process, and the calcium itself, its own concentration, is critically regulated by intracellular processes in order to control these release events.